Are you guys excited to be done science pretty soon? Okay. Pretty soon. Pretty soon. Today and tomorrow, we're done. I think tomorrow I don't know if we'll get it all done tomorrow. It's going to be tight for time tomorrow, but we'll see. All right. So I think that's where we are right now. Yes. Okay. And so again, when we go from a solid to a liquid or liquid to a gas, we got to put energy in to boil that substance or to melt that substance. So energy is being absorbed. We're putting it in. If we're going the opposite way, so if we're going from a liquid to a solid, if we want to freeze something, like for example, let's say you want to freeze some water in your fridge, you've got to take energy out, and the fridge does that, of course, and then freezes the ice, freezes the water into ice cubes for you, for your drinks, okay? Or gas to a liquid, bonds are formed, so energy is released, and you need to cool down the water in order to freeze it, take energy out, okay? Okay. Okay. Now, phase change at a constant temperature. So when bonds break, or if they form during a phase change, the temperature of the substance does not change. Okay? And that's really important for us today here. And we're going to talk about that and what we're going to do with that. Okay? All of the energy is used to create or break bonds and is not available to increase the kinetic energy or the movement of particles, and therefore the temperature remains constant. Okay? And we're going to tell you this again, so I can't stress enough. When we're breaking bonds, so let's say we're going from a solid to a liquid, when we're breaking bonds, the temperature actually doesn't get any hotter. Okay? The temperature doesn't increase. That energy is all going to breaking the bonds first. Okay? So, or if we're cooling it down, all the energy is being released while bonds are being formed. Okay? So, something to keep in mind there. Okay? When we talk about the hydrologic cycle and climate, water molecules undergo many phase changes during the hydrologic cycle. These phase changes include a transfer of energy, but the temperature, again, does not increase during this transfer. This helps to keep the average temperature of the Earth relatively stable. Okay? Okay? This is exactly what we talked about yesterday. That's how these two lessons are very similar. Okay? And we're going to see some similar ways to calculate things. Yesterday we talked about what's the difference between, for example, Vancouver, Victoria, and Saskatchewan, for example. Right? We talked about large body of water. Well, around Earth, there is a large body of water that's called the oceans, yes? There's the Pacific, the Atlantic, what's the other ones? Antarctic, or Arctic Ocean. What's the other one? Arctic, yeah. Indian Ocean, okay? So there's lots of different, like we have a large body of water, yes, all around us. And that's what helps keep the Earth relatively stable. Because what happens is we go through what we call phase changes. So these phase changes, if we didn't have the water, it would heat up and cool down very quickly, okay? But because we have these large bodies of water, like we talked about yesterday, lots of energy goes into the water, lots of energy comes out of the water at times, okay? And that kind of keeps things more consistent. It kind of keeps it more somewhat like, you know, if you're living in Vancouver, it's a little more consistent as far as the temperature goes, okay? that also has to do with phase changes. So not only from, like, for example, from ice to liquid to water, gas, and back and forth, those take energy. That takes energy for that to happen. But the temperature doesn't actually increase during those phase changes. Okay? So if we're going from a solid to a liquid, there's energy that's being put in, but it's actually not increasing the temperature. Okay? We're just changing all those bonds is what we're doing. We're breaking bonds and reforming bonds and things like that. So the first term we're going to look at today is called heat of fusion. Okay? Fusion means melting or freezing. I would write that down somewhere. And I'll let you guys copy what it says here as far as what the heat of fusion is. Okay. Might as well pause it here for. So, it says here that heat of fusion of a substance is the amount of energy required to change 1 mole of a substance from a solid to a liquid. Now, when we do this, we're going to do water. Okay, that's going to be our kind of go-to here. We're going to look at the heating curve of water, basically. Okay, it's not really a curve, I would say, but the heating graph of water. Okay. So when we change it from a solid to a liquid, okay, and if we actually did this, you would see kind of what the graph, what it's going to look like here. But you would see some flat spots there because those flat spots don't actually increase in temperature. All that energy is going to change bonds. So we need to change the bonds we need to break all the solid bonds to make them all liquid bonds. Okay? So the temperature remain at 0. All the energy will not be used to break forces between the water molecules or whatever, for that matter, and not to increase the temperature. Okay? The other term we're going to look at is something called heat of vaporization, which is exactly the same. Okay? Except now we're going to be talking about a liquid to a gas stage or phase. Okay? So liquid to a gas, called the heat of vaporization. Again, if we were going to boil some water, okay, and we started like, let's say 50 degrees Celsius, and we start adding energy, and when we get to 100, it's going to level off for a period of time because we need to put that energy not into increasing the temperature. That's not going to happen. We need to put that energy into breaking liquid bonds, okay, into gas bonds, basically. Okay, so there's going to be a time there where the temperature is not going to increase. Okay, now we're actually just going to skip this graph here real quick. So I'll come back to this in a second. Okay, this is kind of what we're going to be looking at today here. Okay, but we'll come back to this in a second. Okay, for the rest of this lesson, let's see here. I'm going to go to here. Okay, so we're going to skip down to the calculating heat of fusion part on the back side here. Okay, and we're going to copy down this formula. Go ahead. I also want you to write down, now this is how we calculate the heat of fusion. If we were looking for the heat of fusion, for example, we talk about H fusion. Okay, this would be just a variable. This is called the heat of fusion. It's the energy, Q, okay, thermal energy. It's measured actually in kilojoules, so we're going to have to be aware of that. And this is N, which of course is from chemistry, which is mass over molar mass, yes? So that is back to moles again. So basically we're going to get kilojoules per mole, okay? I'm going to rearrange this formula real quick here, and I'm not going to spend a lot of time on that, but I also want you to write down this one. If I wanted to calculate the amount of thermal energy, okay, So if I wanted to calculate the amount of thermal energy, I could also use this to do N times the H fusion. Okay? And that would give me the total amount of energy that I need to put into this, okay, into this system here, into this phase change. Okay, so we'll also copy that down here. Okay. We're going to do the same thing with the formula is exactly the same, just like this one here. We're going to do the exact same thing. What about the calculating the heat of vaporization? Well, exactly the same thing here. Okay, so go ahead and write that down. And again, I think what I'll do here is right now, I'll just put in here, Q is equal to N times H vac. Okay. All right, so go ahead and copy that. And then we're going to go back to the graph here eventually, and we're going to talk about some different parts to this graph and what we need to do where. Just real quick here, just a quick little reminder. It says if we do not know the number of moles, we use N equals little m over big M. Okay, make sure. Little m over big M. Remember, that's the mass in grams. Big M is the molar mass, don't forget. I guess I'll write this down. That's grams. This is what we call the molar mass. Where do you find the molar mass again? Periodic table. Okay. I'm going to give you a little tip here. We're only going to do water. So if you know the molar mass of water, which is what? Somebody quickly. Molar mass of water. No, you should have this memorized by now. 18.02. Okay? So we're only going to use water. Okay? But, again, we could do this with anything. You could do this with anything. But we're going to use water. We're going to focus on water because we're talking about hydrologic cycles and things like that. So that's what we're going to focus on. Okay? Go back to the heating curve and let's take a look at it and see. Oh, I guess I have it right down there. Perfect. So I didn't need to really write that down. That's even better there. Okay. Maybe do you guys need to write that down though, just for review? That's better than what I wrote up here, probably anyway. Okay. I'll let you. Do you need to copy that? I don't know if you do or not, but if you want to look it back. Okay, so don't forget N is the number of moles, which we call MOL, mole. Little m is the mass, so we measure that in grams, of course. Big M is the molar mass, and that is grams per mole. You're going to find that on the periodic table. In our case, it's probably going to be water in most cases. Like 99.9% it would probably be water. So we're going to talk about 18.02 grams per mole there, probably. Okay? Because that's what we're going to be interested in this unit. Good? Everyone good? Yes? No? Okay. All right. Now, we're going to go back to the graph here. So we're going to go back up to, actually, I'm not going to go to this one because I think that one has the answers. Let's go back to this one, which doesn't have anything on it here. So let me just make this a little bit bigger too here. Right here. Okay. So let's take a look at this. Okay. And this is the important part here today. And this is what we need to be able to calculate, things like that. You have to understand what's going on here. So if I started at minus 20 here, okay, this is exactly what you would probably see if we actually did this. Okay. So if we grab some snow, for example, and we packed it together like in a big snowball. We put some heat underneath it, and we put a thermometer in there. Okay, this is kind of roughly what you would see. It would start to increase in temperature. So we're going to go from minus 20 to 0. Okay, what best describes that part of the curve, just from minus 20 to 0? It says you have a couple options here. Okay, let me ask you this. If we were doing this part right here, do you think yesterday's formula would apply to that, or do you think one of the ones from today would apply to that? So think about this. Q equals MC delta T from yesterday, or one of the ones today where we're talking about a phase change. What do you think? Yeah. Probably the one from yesterday. Okay? So the one from yesterday involves the temperature, delta T, yes? Right? So there's a change in temperature that's taking place. So this right here would be best described by Q equals MC delta T. Yes? Okay? There's a temperature change. We're going from minus 20 up to 0 in not very much time, in like a half a minute roughly, yes? Okay? Roughly. Good? Okay? Now I'm going to skip the next part here. Let's talk about this part right here. I'm going from here to here. Do we have a temperature change there? Yes or no? Yes. Okay? So again, I would probably want to use Q equals MC delta T. Okay, there's going to be a change in temperature there, yes? Okay, I'm going from, look, 0 up to 100 degrees Celsius. Now, in fact, in this case, delta T would be 100, yes? Right? Okay. Now, we didn't keep this going for forever, but look, if I talked about this part right here to here, is there a temperature change there? Yes? Okay, so we want to use Q equals MC delta T. Yes? Okay? In fact, that temperature change is what? I guess that would be what, 160 here, yes? And that would be 100, so we're looking at 60 there, yes, for a temperature change. Okay? Does that make sense, guys? Yes? No? Questions? Okay? So we're talking about different substances here. Obviously this is all has to do with water, but this is actually what? Ice here, yes? This would be liquid water in this middle section. And then of course over here we have steam, okay? So we got 3 different sections, and we'll talk about what that means for us as we go along here, okay? However, okay, so look, if I actually was doing this, do you have to put energy into this, or would you be getting energy out of this? You're putting energy in, yes? So again, let's say we're in the lab and we have a solid chunk of ice and it's at minus 20 degrees Celsius, and I put a thermometer there, and of course I'm going to start heating it from the bottom. I'm going to start putting energy in. What happens in this section right here, though? Notice, this is actually what you would see. There is no temperature change, right?
This is like where we're changing states. Is this where you use the other formula?
Absolutely. This is where we're changing states, okay? So if you actually did this in the lab, for the first half a minute, it would increase in temperature, yes? Roughly. And then from here to here, there's going to be a period of time where the temperature actually does not increase. And you might say, well, I find that hard to believe. Again, it may happen fairly quickly. But minus 20 to 0, and then we're going to get stuck at 0 for a bit. Okay? And what's happening there is we're changing all the bonds, right? We're changing the solids that are locked together. We have to put enough energy into them so that they can kind of break free and start to move back and forth. Okay? So that takes some time, and that takes some energy. So right here, in that section right there, do we have a temperature change in that section? It's flat, right? Look, there's no temperature. It's stuck at 0. So if I did MC delta T, what's delta T? 0. Well, what's 0 times that is 0, yes? So that doesn't make sense. So now we have to use a formula from from today, I should say. And we're going to use this one, Q equals N. Now, is this called heat of fusion or heat of vaporization? Fusion or vaporization? Fusion. So I'm going to use this formula here, N times H fusion. Okay? And that's going to tell me the amount of energy I need to put in to change it from a solid here, okay, solid. We're going to start to break some bonds, break some bonds, break some bonds, break some bonds. Now we've turned it into a liquid, okay? So that's the amount of energy I need to change the solid into the liquid. Okay, that's called the phase change. And then when we get to this other part here, notice right here, Okay, again, we have a liquid here. We need to put in energy, 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 energy to turn it into a gas there. Okay? Again, there's no temperature change here at 100 degrees Celsius. In fact, it actually becomes a little bit even harder to boil water. So it's going to stay pretty consistent at 100 before we change enough of those molecules into liquid state, into gas state. Okay? This is, of course, the heat of what? Vaporization, yes? So that's where we get the HVAP there. Okay? And I always remember it this way. I always think, if I get confused between fusion and vaporization, most of us probably have heard the term vaporize, right? It means to turn into a gas kind of thing, you disappear. So I always remember that vaporization is that one there because we're turning it into a gas. So fusion is the other one where we talk, if you're fusing things together, you're making it into solid, or kind of you're breaking up the solid kind of thing. So that's how I kind of remember it there. So we kind of have 5 parts to this graph, right? 1, 2, 3 on this angle thing here, 4, and then 5, yes? Okay, 5 different parts to this graph. Okay, and we're going to get to how do you calculate these numbers here, so we're going to get to that in a second. Okay, good? Okay, next. Let's see, that's not the right one. Let's see. Okay, so now we're on to examples here, I think, and I don't know if I can erase this or not. Nope. So let me go to here. Okay. So now we have 4 examples to do here. Okay, and these are going to be super important here for yourselves, and they start on the 3rd page here at the top. Okay. So here we go. Example 1. It says here when we have 27.14 kilojoules of thermal energy is added to 4.5 moles of ice at 0, the ice completely melts. What is the heat of fusion of water? Okay, so they want to know what is the heat of fusion of water. Okay, now this was one of the formulas we copied down today. Okay, again, listen to this closely. We have 27.14 kilojoules of thermal energy. 27.14 kilojoules of thermal energy, that's Q. Okay, and we have 4.5 moles, that's an N. And here's the important part you have to understand here. Look, it says of ice at 0. The ice melts completely. Okay? Does the temperature change here? No. Okay? What's it going to change to? It doesn't even say. There's only one number here, it's 0. So water's changing basically states here. Okay? So when we're changing states, we're using one of these formulas here, like H fusion, Q, N kind of stuff. Okay? What is the heat of fusion of water? So look, the heat of fusion was given by that formula there, Q over N. Okay? And all we need to do in this case here is put in the 27.14 kilojoules and the 4.5 moles. And we're going to get this answer here, which of course we're just going to divide those two. Give me one sec here. Come on. There we go. 27.14 divided by 4.5, and we get what? 6.03 kilojoules per mole. Okay? And those are the units we're going to stick with because heat of fusion is measured in kilojoules per mole. Okay? Well, that's all we need to do for that one. Okay? There's nothing really too fancy about that. So we just have to remember, and by the way, these formulas are on the back of your periodic table. Okay? So just remember that. They're there. Okay? Now, let's take a look at the second example here. Is that good for everybody? Everybody got that? Okay? Make sure you have these. It's going to be important for you. Example 2. Okay? If you had 5 grams of ice, so that is a mass, yes? You got 1.67 kilojoules of energy is absorbed. Calculate the heat of fusion. So again, we want to calculate the heat of fusion, and I know that that formula is, it looks like that. Okay, heat of fusion. Again, there's no temperature change here. Okay, it says when 5 grams of ice melts. Okay, so again, we're starting at 0, and we're ending up at 0. It's just we're going through a phase change. Now, this one becomes a little bit, not a whole lot trickier, but what we have to remember is we got 1.67 kilojoules here, but N is something we're going to have to calculate this time. And of course, to calculate N, we've talked about this earlier today here. We're going to use this formula here, mass and molar mass. My mass here is 5 grams. My molar mass is 18.02 grams per mole. And again, that's water, right? So water is 2 hydrogens and an oxygen. Look it up on the periodic table. Okay, 2 hydrogens, 2.02. Oxygen is 16, so 2.02 and 16 is 18.02, right there. Okay, I'm going to divide those two, and that's going to tell me how many moles I have here. So let's see, what is that? 5 divided by 18.02. 0.2774 moles. Don't forget that's going to go here. Don't round it, of course. Okay, that's my N. And I'm going to divide those two numbers. Okay, so 1.67 divided by that answer there, which is 6.02 kilojoules per mole. Okay, 6.02 kilojoules per mole. Now, I do need to get your periodic tables out. So let's get those out. I want to bring some things to your attention here. Okay, we're going to look on the back. Okay, is that good? Any questions on this one here? Questions? Anyone? Okay. Let's look at example 3. It says this. How much energy is absorbed? What letter are we looking for? What do you think?
Q.
Q. Okay. So how much energy is absorbed? What are the formulas that we know for Q? Well, we know MC delta T, yes, right? That's when we have a temperature change. We also know that I wrote down some formulas on the board today, which was just kind of the rearrangement of H fusion and H vaporization, right? So we have also Q equals N times H vap, or Q equals N times H fusion. Kind of depends. Okay, let's take a look here. When 335 grams of water is boiled. Okay? Now, that's all they tell you. They do tell you this part here, but let's just even ignore the refer to the data book, but you guys don't even have a data book, but you guys have a periodic table. Okay? But let's just ignore that part for a second. How are we going to find Q? Okay, well, let me ask you this. If I'm boiling water, should I use this formula here? No. Okay. First of all, what's the temperature change going to be? Well, yeah, it'd be 0, because we started at 100, we ended up at 100. We're just changing the bonds, right? So that's not going to work for me, so I can't use that, right? Does that make sense? We're not increasing the temperature of the water or the gas. We're trying to get the water into a gas, which requires energy, but there's no temperature change. So I can't use that. So I guess we have to talk about N, H fusion. Is that the right formula? That's if I wanted to change a solid to a liquid, yes. Okay. We want to talk about boiling, which turns it to a vapor. Okay. And that's how much energy I'm going to need to do or put into this to change it from liquid to gas, yes? I'm going to boil 335 grams of water. I'm going to change it into a gas. So, what's N? Do I have N? No. But can I find it? Yeah. I can do this thing again here. N equals little m over big M. 335 grams of water. 18.02 grams per mole, right? Periodic table. And I can divide those two, and I should get, let's see, 335 divided by 18.02, and, 335 divided by 18.02, and I get 18.59 moles. Okay? Ish, roughly. We're not going to round, of course, because that's not my answer. That's just that's the amount of water I'm trying to change. So I'm going to go up to here, and I'm going to say, okay, that's 18.59 moles. Now, I'm looking for Q, right? How much energy is required to do this? Well, the problem is I only have that number so far, okay? But we have to also understand that there's always going to be some constants involved here as well. Now, we actually found these constants. If you went back to here, we found out that the heat of fusion of water is usually 6.02 kilojoules per mole, which is actually one of the constants on your periodic table. So find that on your book. It's right there at the very bottom somewhere, probably. At the very bottom, you're going to see that there is, in fact, a heat of fusion of water. It's about 6.02 kilojoules per mole. This one was a little bit off, so this would have been, this is 6.03, but it was a little bit off of what we expect to see. What's the heat of vaporization of water? What is that number? Yeah. Kevin? Sorry, what? 44?
Yeah.
Yeah, 44.0 kilojoules per mole. Okay? So basically it takes 44 kilojoules of energy to basically turn 1 mole of water into a gas. Okay? We have 18 moles of water, so we need to put in 44 kilojoules times 18 moles to figure out how many kilojoules of energy we would end up with. So if I go back to here, I'm going to take this times 44, and I get 817.98 kilojoules of energy. Okay? Now notice, I'll round it here in a second, just wait. Notice this says kilojoules. Okay, so I want you to pay attention to that because that's what these are measured in. Okay? I think we need 3 significant digits, if I'm not mistaken, from this here. So let's go to 818 kilojoules. Final answer. Okay? Is that good? So quite a bit of energy if you want to boil 335 grams, which is 335 milliliters. If you wanted to boil 335 milliliters of water, you'd need 818 kilojoules of energy to be put into that, to change it completely from a liquid to completely a gas. Okay? That's how much energy you would need. Good? Okay, questions anyone on that? Yes, no? Okay. Now our last example is definitely something you're going to see here. Okay, now listen. This, example 4, notice it says here, and you need to pay attention now that we talked a lot about, what happens if it stays the same, right? Now we're going to combine yesterday and today together. So we're going to talk about a temperature change, but also staying the same. So here we go. How much heat would be required to raise the temperature of 30 grams of water from 75 to 125? Okay? Now usually this next part's not going to be there. But what I like to do with this is make a little graph. So let's start with a graph. Okay, please do so. Somewhere. Doesn't have to be like super big, but please make a graph. Okay? And we know that when we heat up water, and I'm just going to make this 75 here. Okay? When I start to heat up water, is it just going to go straight up to 125 here? So is it going to look like that? No. Okay? So we have to remember that we need to take a break here. Okay? So we're going to go from 75 to 100 because at 100 we're changing the water into a gas. So we need a flat portion here where there's not going to be a temperature change and then where there's going to be another temperature change there. Okay, does that make sense? Okay. Now, here's how this, we haven't done this part yet, so this is where it becomes a little bit different. Okay. And I like to kind of label these parts here. So I call this 1, I'm going to call this 2, and I'm going to call this 3. And they talk about how there's 3 different parts to this graph. Yes? Okay. So I like to kind of label them. And now I know kind of, okay, this is what I'm going to do here, this is what I'm going to do here, this is what I'm going to do here. Okay? So let's look at part 1 here. What formula best describes that part of the graph? What do you think? Yeah, Cayman. Why? Exactly. There's a temperature change, so we want to use Q equals MC delta T. Okay? Good. Now, what is the mass that I need to use? I think that's my question, yes? 30 grams, yeah? Okay, so let's use 30 grams. Now, what is C? What is C? You tell me. What is it, Elliot? 4.19 joules per gram degree Celsius. So just like we did yesterday kind of thing. Joules per gram degree Celsius. What's the temperature change here for this? What's the temperature change? Yeah, John?
15.
Nope. 25. 75 to 100. 25 degrees Celsius. Okay? We are going to get a Q value for this. So let's go ahead and do that. Let's see. 30 and 4.19 and 25. 3,142.5. 3,142.5 joules. Yes? I'm just going to leave that number for now. I'm not going to round it or anything like that. I'm just going to leave that number. Is that good for everybody so far? Yes or no? Okay. Now, questions? You know what? While I'm kind of on this roll here, okay, I'm going to skip 2 for right now. I'm going to actually go to 3. Now, you can do 2. There's no, that's how I kind of like to do it, but that's just me, okay? You do what you do. If you want to do 2, you go ahead and do 2. I'm going to skip to 3. Now, what formula should I use here for 3, section 3? Yeah. Right. Why? Right. Change in temperature. Okay, good. So again, we're going to have 30 grams. If you got 30 grams of water, okay, and we're changing that, we're increasing the temperature, that's fine. Okay. Now, here's the issue though, and this is the important part. What's C? Yeah. Elliot?
2.02 grams per joules per gram.
2.02? Why? It's steam now, yes? So we don't have water anymore. This is actually what? Anything over 100 is steam or water vapor, yes? So it heats up differently than water does. And ice has a different heat capacity as well. Okay? So we have to remember that. So don't get just don't start plugging in 4.19 because I've seen that number before. Now it's 2.02 because it's actually steam in this section right here. So 2.02 joules per gram degree Celsius. What's the temperature change here? 25 again because I'm going from 100 to 125. Okay? I'm dealing with this graph in different sections. Okay? So I'm going to multiply those numbers together now. 30 and 2.02 and 25. 15, 15. And Q equals 15, 15 joules. Okay? Good so far? Okay. Now, we got to talk about section 2. Because remember, I'm putting energy, in fact, I'm putting 3,142 joules of energy in. I have to put energy in here to transform it from a liquid to a gas. And then the last part here apparently is 1515 joules of energy that I need to heat up the steam. Okay. Now we're going to talk about section 2. So section 2, does it make sense to talk about this for section 2? So there's no temperature change, so that would be 0, right? So we can't use that. We want to use what? H fusion or H vaporization? H vaporization, yes? So I'm going to do H vap. Okay? So I'm going to use this formula here. I want to calculate the amount of energy that it's going to take. Now, I'm going to do this in one step if that's okay. If you're not happy about that, that's fine. But really remember, N is equal to little m over big M, yes? So instead of putting N here, I'm just going to write in 30 grams of water that I need to change into gas. So, and again, water is 18.02. Okay, we still have water. So it's 18.02 grams per mole. So this is my mass over molar mass here, yes? Okay. If you want to do it separately and then put the N value in, you can most certainly do that. I'm going to cheat a little bit and save a little bit of time. What is the H vaporization number again for water or steam, basically? What is it? How much? No, that's C. What's H vaporization?
44.
44 kilojoules per mole. So we have to make sure we're using the right constants there, yes? Okay, that's your H vaporization number. Now, Q, when I go ahead and do this, so what do we got here? 30 divided by 18.02. So I'm going to try and heat up, basically, or I'm going to try and change 1.66 moles of liquid into 1.66 moles of steam, yes? Gas, phase change, okay? And I'm going to multiply that by 44 because it takes 44 kilojoules of energy for every mole. So this is 73.2519. 73.2519. But here's the important part. That is measured in kilojoules. Okay? So when you get these heating curves, we call them heating curves, okay? You have to understand that the delta T's are in joules, but the other ones are not. Okay? Yeah. Okay, does that make sense? So these are in, like I said, these are in joules, and this is in kilojoules. So we make, now you might say, well, what do I do here? It's up to you. I don't really care, but we need to get them, make sure they're in the same unit. What's the total amount of energy I need here? Well, I need to add up 1 and 2 and 3. Yes? I need to add up those 3 sections. Okay? I need to add up those 3 sections. So I need to get the same units. I think it's probably going to be easier to change this into kilojoules, change this into kilojoules, use this in kilojoules as it is, and then just add those 3 together. Okay? So right here for 1, I'm going to actually say what? 3.1425 kilojoules plus 1515, so that's what? 1.515 kilojoules plus 73.2519 blah 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 kilojoules. Okay? I'm going to go ahead and add those up, so I'm going to change them all to kilojoules and then add them up, and my answer will be in kilojoules, and that's okay. All right? So right here, I'm going to go what? There's my kilojoules answer, so plus, what did I do here? 3.1425 and 1.515. So I get a total of 77.909 kilojoules. Okay? Or I think we have to kind of go back to default here. And remember, if we're multiplying and adding, we got to go back to multiplying rules. So I think we can only have 2 significant digits all said and done. So I'm going to call this 78 kilojoules would be the total amount of energy that I need to use there. Okay, does that make sense? Okay? Is that good? Okay, questions? So you add them up at the end. Again, we have to make sure we get the same units though. That's probably one of the big mistakes there. And we also have to talk about, 3 different sections here as well. Okay, any questions? Okay. Now, real quick here, we're going to do one more thing just before we forget. Okay. And I want you to just copy this down as well, maybe. Okay. Good? Okay, everyone got that? Okay. Now listen. Let's say this was minus 40. Put 0 there. 100. 150 or something. Okay. Just copy this down with me here. Okay. So, yeah, sure. Yeah, we'll go from there. There. Okay. Oh. I think you're coming back. So, listen, we are, if we get this curve here, okay, listen, we have to do what? Quite a bit more to this graph, yes? Okay? We should have what? 1, 2, flat part, 3, 4, and 5, yes? We have 5 parts to this graph, okay? Something to consider. Yes? I don't know what this now. I kind of did that on purpose, but I don't know what this number is here. This is, by the way, straight here. Okay. I don't know what that. I don't care. I'm not going to do this, but I'm just saying there's 5 parts to this graph. Okay. For 1, you're going to use Q equals MC delta T. Now, what would you have to know about this part here? Somebody. You will know the temperature change because there will be a temperature change, and you're going to know the mass and what?
You need to know C.
C. Is there a different value for C for this?
Probably.
Yes. Look on the back of your periodic table. What is it? You're going to have to know the value of ice. Yes? And I think is it 2? Exactly. Okay? So this is, again, remember, 2 joules per gram degree Celsius. Yes? Okay? Part 2. Okay? So part 2 here. Q equals what? NH fusion, I guess it would be, yes? Is that right? Do you agree? Okay. And H fusion, of course, you're going to have to know that. That's a constant as well. That's what? 6.02, I think. Is that right? It says that. But remember, this is measured in kilojoules per mole. Okay? Then we have section 3. Q equals MC delta T again. We got a temperature change, yes? Okay. What's C for this? What do we have to keep in mind here? C is what? C of what? Water. Okay. And that is what? 4.19. Okay. That's the one we kind of remember, of course, because we've done that one before. Okay. And then again, we're going to have section 4 here, which is Q equals NH vaporization. What's the H vaporization number? We've done it already a couple times today. Huh? 44 kilojoules per mole. And then we're going to have section 5, and we're going to have a temperature change again. And that, of course, is, C, but that'll be of steam. And then what's that number? 2.02, all right? So 2.02 joules per gram degree Celsius, okay? So a lot to consider there, and notice it's not always going to be the same, okay? Now, I'm going to tell you one thing real quick here, and then I'm going to be quiet. You guys can do some work here because I'm sure you got some examples to do there, or some homework. Listen. couple things here. Has everyone got that okay? Yes? Okay, make sure you copy that down so you know. If I gave you this question, whether it's on a unit test or a final exam or whatever, how many marks do you think this is going to be worth? Ballpark it for me.
25.
10, yeah, maybe 20, probably not 25, that's maybe a bit much, but probably like 10, yes? Okay? Right? Do you agree? It's going to be worth a little bit. There's lots of stuff to do here, yeah? Okay? So look at the question. When it says 10 marks, I'll give you a good way. I'll tell you, if it's worth 10 marks, or maybe 12, or maybe 15, okay? You've got some work to do, right? Like there's going to be some work involved. That means that you probably need to do something like this, yes? The biggest mistake I see when I give you this question someday, whenever, okay? If I do, and I probably will. But when I get when I give you this question, here's what people want to do. They want to do this. So let's say we start at, I don't know, I'm going to actually start this one at minus 40, and let's say we go to 150, okay? And this is what I see. I see this. Q equals MC delta T. Do you think that's worth 10 marks? Come on. Like, really? Yet I say this, and yet I still have people do this, okay? You can't think that I'm just going to plug in 20 times 4.19 or whatever number. You can't even choose that because you got 3 different states going on here. And the temperature change is what? 190, I guess, yeah? Is that worth 10 marks? No. Okay? So look, you have work to do. Okay? That's what I'm saying. You can't do this. If you do this, guess what your mark is out of 10? No, it's 0. Because what am I going to do with that? Like what? I'm going to give you a mark because you know the right mass? Well, yeah, it's in the question. Am I going to give you a mark for C? No, because it's wrong. Because we got 3 different parts to this graph and you assumed it's all the same. Am I going to give you a mark for temperature change? No, because you got it wrong. So you're going to get 0 out of 10. Okay? You can't do that. Okay? This is obviously this is not 10 marks here. Okay? So what you have to remember is if it's worth 10 marks, you know, is this worth, I don't know, you know, that's maybe worth 2 marks, you know, right? I mean, that's Q equals MC delta T. That's all you need to do there, yes? I mean, that's a 2-mark question, if you want a 2-mark question. But if that's all it was, fine. You know, we can plug in mass and C and T. Make sure you're using it for ice, of course. But, you know, we have to think, okay, I need to do probably something like this, because Bachek, you know, he loves us, but he's not going to give us 10 marks for just writing Q equals MC delta T. That's silly. He doesn't love you that much, okay? So you have to keep that in mind. There's many parts to this. And now, will it be 5 steps? I don't know, okay? Maybe it won't be. Maybe it's just going to be 3 steps, right? This one maybe wouldn't be. This could be a 10-mark question, I guess, if I, you know, said, okay, I'm going to give you 3 marks for this and 3 and 3, I guess, you know, and I'm nice to you or whatever, and then put a mark in for the final answer or something like that. Yeah, maybe 10 marks, okay? Probably more like 8, maybe, or something like that, maybe for that, or 7, somewhere in there. But again, you know, you have to think about where you're starting, and where I end up, and is there any flat parts in there, okay? And if there is, okay, I'm starting here, there's a flat part. I'm starting flat part, and I end up there, okay? You know, this one here. If I'm just doing this, okay, perfect. There's only one section I got to worry about. But if I'm going to go from minus 40 to 150, I got lots of little parts in there that I need to be aware of. Yeah? So keep that in mind. Okay? Temperature changes, we use Q equals MC delta T. Flat parts, we use Q equals NH fusion, NH vaporization. The only thing that kind of tricks you up a little bit is if they say, let's calculate the H fusion, Or let's say they tell you what the H fusion is. So they say, okay, the H fusion is what, 6.02 kilojoules per mole. And let's say they tell you, well, they could maybe tell you N. Okay, let's say it's 4 moles. No, that's not a good question. Let's say they tell you Q. Let's say it's 27 kilojoules. Okay, could you figure out N from this? Is that possible? Yes. Right? Could you figure out the mass from that? Yes. If you knew the molar mass, yes, which is probably going to be water, because we're obviously using water, 6.02 kilojoules per mole. Okay. So it kind of those are the questions that are going to be a little bit more trickier, perhaps. But just kind of keep that in mind when you're thinking about these things. I'm not going to say anything more about that. Okay, good.